So here we're going to do the binomial probability formula. This is the probability exactly X successes in N total trials. This is equal to the probability that the probability that X is equal to N factorial divided by N minus X factorial times X factorial. By the way, this right here is the definition of N choose X. Okay, so N objects chosen X at a time. And then this is multiplied by P, the probability of success raised to X, multiplied by Q, which is raised to the N minus X. Okay, so what do these things tell you here? All right, this first part right here, as I just said, this is N choose X, which means how many ways I can rearrange X number of successes if I have N total trials. All right, so the number of objects rearranged, X number of successes out of N trials total. This is the probability of success raised to the number of successes. Okay, that's what that is. And then this right here is the probability of a failure raised to the number of failures. Now, how I want you to think about why this is the number of failures, guys. Look, if I had N successes, so success, success, success. I'm sorry. If I had X successes and then fail, those are failures. But when I add all these up together, I get N total. Well, what is this piece in right here? Well, that piece, let's call it Y to solve for Y minus X from both sides. So this is equal to N minus X. So this Y here, okay, is technically N minus X, okay? And so that's how many total failures there are. X is how many total successes there are, okay? So that's where this number of failures comes into play. That's where that number of successes in total trials. All right, so that might be kind of confusing, to say the least, okay? So let's try it with an example. Let's use the example where we had a procedure. Okay, there were 6 surgeries, right? So 6 surgeries, and then there was a 70% chance of success for each surgery, right? And the surgeries are independent of each other. And I want to find the probability that there were exactly 0 successes. What does that mean? No successes. That's a probability of a failure, and 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 a failure. Well, since it's binomial, they're all independent of each other, right? Each failure is independent, so I multiply probability of failure times probability of failure times the probability of failure. And I do that, I write that out 6 times, right? Okay, what is the probability of a failure? Well, if the probability of success is 70%, the probability of a failure is 30%. So I'm going to write out 30% 6 times. Okay, there is a better way to do this, and that's to write 0.3 raised to the 6th power, because I have it written 6 times. And if you do that, you're going to get 0.000729. Okay, 0.000729. Now, say I want to, and there's only one way to get all 6 failures, right? So only one way that I can get 6 red failures. Now, say I wanted to do the probability of success is equal to 1. So there's 1 success. So maybe this is probability of a success and then fail, 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 fail. That's a bad day, right? So what is this? This is a probability of success. And then I have 5 failures. Okay, then I have 5 failures. So what's that equal to? It's 0.7. And then I have 0.3 raised to, well, how many failures? There's 1 success. That means there's 5 failures. If there's 6 total surgeries, these exponents have to add up to 6. Okay? Technically, if you think about it, there are 0.7 raised to the 0 because there's 0 successes. If there, see, we had 0 successes. Okay, so that's kind of technically using the formula. Now, how many ways can I rearrange all failures? Well, if I plug that into my formula, my goodness, right? That would be n factorial, so that'd be 6 factorial over what? 6 factorial times 0 factorial. Well, 0 factorial is equal to 1, okay? And so you have 6 factorial over 6 factorial. If I divide something by itself, that's always 1. That's why there's only one way to rearrange all those failures. But what if I have 5 failures and 1 success? Is that the only way to do it? No, you could have a failure, success, then fail, 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 right? Is that the only way that you could do it? No, you could continue this trend and push the success all the way through until you got to the end. And so these would be the scenarios, all the different scenarios that are possible. You could have the failures be in all those positions there. Okay? So those are the different ones. How many are there? There's 1, 2, 3, 4, 5, 6 total. So how do I know this a little quicker than writing it out? So instead of adding this 6 times, I'm going to multiply that whole thing by 6 because there's 6 of those ways to do it. Okay? There's 6 ways we can get 1 success. How do I know? N factorial over n minus x factorial x factorial. What does x equal? X equals this 1 here, right? So x is equal to 1 success. So that means 6 factorial over, well, what is it? 6 minus 1 factorial times 1 factorial. 6 minus 1 is 5. So 6 factorial over 5 factorial. 1 factorial is 1. So this ends up being just 6 times 5 times 4 times 3 times 2 times 1 over 5, 4, 3, 2, 1. And the 5s cancel, the 4s cancel, the 3s cancel, and the 2s cancel, and all I have left is the 6. And that's where that 6 total comes from. So you see how all you're doing here is you're taking what? You're taking your 6 positions, 1, 2, 3, 4, 5, 6, okay? And you're dividing out the 5, scratch that. Okay, so you're doing n choose x. So n choose x here, combination, okay? So you're 6 objects and you're choosing 1 success out of those, okay? Meaning if I just take this scenario here, I can't tell the difference between those 5 f's, so I have to divide out the 5 factorial there, okay? And so that's what's happening. I'm dividing out the 5 factorial there. Dividing out that repetition. Okay, so when I multiply this out, what do I get? I actually get 0.010206. Okay, to show you in your calculator, I would do 0.3 raised to the 5 times 0.7 raised to the 1. Okay, multiplied by 6, enter, and that's where I get my decimal from. Right? If I did x equal to 2, I could run through that same game there. And just to show you how it works with the formula, okay, to show you with the formula, if x equals 2, so probability that x equals 2, so I have n, which is 6 factorial over 6 minus 2 factorial times 2 factorial. Probability of success is 0.7 raised to the 2 times the probability of failure, 0.3 raised to the 6 minus 2. So that's how I plug it into my formula. And so what does this equal? Well, this will simplify to what? Well, 6 factorial over 4 factorial, 2 factorial. Okay. So what is that? Well, that's 6, 5, 4, 3, 2, 1 over 4, 3, 2, 1 times 2, 1. Right? That's a 2 factorial there. I'm going to cancel the 4s, the 3s, the 2s, and the 1s. And I can actually cancel that 2 with that 6. And so what do I have? I got 15 over 1, which is 15. Okay? So 15. So this is 15 times 0.7 squared times 0.3 to the 4th. I'm going to type that in my calculator. I'm going to get 0.059535. Okay, so that's how you would use the formula, right? Was with the number of 2 successes. Okay? So that's kind of complicated, right? That is kind of complicated, just to say to say the least, right? So I don't want you to have to do that unless you really have to, and there are some homework problems where you have to use this formula, right? So that's the formula, but you can use this using a table. So using table, right? So from the table that will be posted in Blackboard, and you'll see a purple sheet maybe. The table, I want to fill out the probability distribution. So x and p of x. So what are all my number of successes? I could have no success. I could have 1 success, 2 success, 3 success, 4 success, 5 successes, all the way up to 6 successes. Okay? When I'm dealing with 6 trials, 6 successes is the most that you could have. So you need n equal to 6, p equal to 0.7, o, and then q is given because I subtract there. And that's the information I need to use my table. So I'm going to go in and see if I can't find a table. Okay. And so here's what we're going to do. Let me clear this out. All right, so I've got my table I'm looking at here. First thing I do is I start with the n. My n is 6, okay? So the n tells me where to go, so I'm only concerned with these values right here. Those are my x values, the number of successes. Once I have that, I go to my probability. My probability of success is 70%. So this tells me the row to go down, or the column to go down. So this is the set of numbers that I care about, okay? So So the first one represents 0 successes. Okay, so that's, let's see here. So 0.001. The next row represents 1 success, so 0.1, then 0.06, or sorry, 0.01, then 0.06, and then 18 or 0.185, and then 32.4, and then 303, and then 118. Those are the values. So let's plug those into our probability distribution. So 0.010, 0.060, 0.185, 0.324, 0.303, and 0.118. Now look at that. That's way faster. Look, this is the probability of 0 successes. What did we say? The probability of 0 successes was equal to, holy cow, look at that. That doesn't equal 0.001, but yeah, look, the table goes out 3 decimals. 5 or more, raise a score. 4 or less, let it rest. That's why they round it up to 001, okay? If I had probability of success equal to 1, I got this value here. If I truncate it, I cut it off there, all I can see is the 0.010, okay? So that matches that there. And then this probability here, if I round it to 3 decimal places, what happens? 5 or more raise a score, so that bumps this up to 0.060, which is exactly what I had there. So in these numbers here are generated from our probability formula right here with a computer. And that's how it makes that table there, okay? So that table is generated from a computer program that uses a formula that you see right here, okay? So the thing is, though, since it cuts it off at 3 decimals, that's where you see the rounding issue going on here. All right, so that's a rounding issue going on. So sometimes when you're adding everything in your table up, you might get like, that's what I'm talking about, like you might get 0.999 or 1.001. Don't fret, okay? It doesn't mean you're wrong, all right? It's just a rounding error that is actually occurring there, okay? So what I want to do is I want to graph this binomial distribution. And so let's graph it. So at 0, I got a 0.001. So I'm barely going to have anything, 0.001. And then I'm going to have at 1, 0.010. And at 2, 0.060. And at 3, okay, that height, I'm kind of messed up on that. Let me see if I can fix this. Made it a little bit too high. All right, so .185, and then 4. Sorry, they should be straight. 324, and then 5 is a little lower at 0.303, and then 6 is here at 0.118. Okay? Now, what do you notice about this distribution? It looks like it's skewed left. It is skewed left, okay? Skewed left. So the distribution is skewed left. Why is it skewed left? Well, what is our probability of success? Probability of success is 0.7. There's a 70% chance that it's a good surgery. Well, by golly, guys, when you're when you have a 70% chance of it being good, then when you get 6 trials, it probably you're going to do better than average, right? So your average is going to be somewhere around in here. So when your average is looking like it's somewhere around in here, then you do have the possibility of getting no successes, but it kind of skews off. So here's the idea. Since P here was equal to 0.7, if P is greater than 50%, it's greater than a 50% success rate, then you are skewed to the left, okay? If P is exactly equal to 50% chance, is a 50% chance that you are successful and a 50% chance you're a failure, then your distribution is symmetric, okay? Draw a vertical line down the middle. It's the same on both sides. A symmetric for 50%. And if your probability is actually less than 0.5, then what that means is that you're actually going to be skewed right. So without looking at the picture of the distribution at all, and you see that you have a probability that's greater than 50%, you know right off the top of your head that that's skewed left without doing anything. So you might be asked, okay, based off of a probability of success of 70%, what does the distribution look like? You should be able to say, well, the probability of success is greater than 50%, it's skewed left, okay? And the way you think about it is, if you have a higher chance of success, if there's a higher chance of success, that means there's going to be more successes than failures, right? So if you have 6 total trials, and more successes than failures is like 4, 5, or 6 successes, okay? So if I have a probability that's greater than 50%, then I'm going to be in one of these categories is what I would expect. Therefore, my average, where I see most of my data, will be on the right side, but it skews off to the left. Okay, that's the idea. And then it's the exact opposite when I'm talking about probabilities that are less than 50%. If you have if you got like a 10% chance of being right, not many times out of 6 are going to be right. Most of them are going to be wrong. And so it's very skewed to the right in that scenario. Okay?